Hello everyone. We already have covered some topics in this course. Today we will focus on these four topics largely. The first topic is carrier concentration in intrinsic semiconductor. To some extent we already have discussed what is carrier concentration, but we will now elaborate this in this particular lecture. And we will discuss what does that mean in intrinsic semiconductor as well as in extrinsic semiconductor. We sort of explained what is an intrinsic semiconductor and what is an extrinsic semiconductor. So intrinsic semiconductor is where more or less we can consider the semiconductor material to be very pure. For extrinsic semiconductor, we basically dope the intrinsic semiconductor with certain sort of doping molecules or atoms. So in this particular lecture, our focus will be on carrier concentration, how this is different in intrinsic and extrinsic semiconductor. We will discuss the concept of equilibrium, what is equilibrium, how equilibrium matters, and why one should be very careful about this equilibrium condition. Why we actually take equilibrium into consideration, because equilibrium is a very ideal situation, but in practice you will find most of the situations are not under equilibrium, but still we start our discussion from equilibrium condition. We will also discuss the concept of steady state. So equilibrium and steady state to some extent are related, but we need to understand what is a steady state and what is an equilibrium and how they are different. In many of the texts or textbooks, you will find that this equilibrium and steady states are used sometime interchangeably, but there is a difference between these two terms or these two terminologies or these two concepts. It is very important that we understand that difference. So let us move ahead. So to begin with, we will first start the concept called equilibrium carrier concentration. So I already have mentioned that carrier concentration is one of the very important properties of semiconductor that we need to take into consideration. And in semiconductor, if you look at the carriers, you'll find both type of carriers, electron and hole, that is positive and negative. Both type of carriers are possible inside a semiconductor, and that is, you can say, one of the major advantages the material provides. So let us now see how this equilibrium carrier concentration changes, what is equilibrium, and let us begin with the basics of this concept. So before we start understanding the concept associated with this, let us see how carrier concentration changes with temperature. We already have said that temperature is one of the excitation parameters or atmospheric condition which changes the carrier concentration by and large. Now let us see how carrier concentration in an intrinsic semiconductor changes with temperature. So this is a plot that is shown. You can see that the carrier concentration linearly changes with the reciprocal of temperature. So if you look at the axis, you'll find that in the y-axis it's a log scale, and in the x-axis it's reciprocal of temperature. So this is something like the log of carrier concentration is linear with respect to reciprocal of temperature. So if you write y equal to mx plus c, it's something like that. Now what is our target? Our target is to figure out what is m and c. We will see how why the concentration is varying linearly. I mean, with respect to reciprocal of temperature. We will see this, but this is more or less the trend. So if you see the plots, these are just roughly I have shown. If you see the plots, okay, these are not the exact plots. Okay, just to give you one trend, a feel, I just have drawn on a piece of this slide just to give you the idea. So for different material, the change in the concentration is different, right? And in this case, at room temperature also, you'll find that concentration of carriers in each material is different. The right hand side in this case is low temperature, left hand side in this case is high temperature. You have to remember that because it's a reciprocal of temperature 1 by 1000 by T. So definitely you go right side, it's a low temperature because this value will increase if you decrease T, right? So that's why right side is high temperature, right side is low temperature and left side is high temperature. So I also have, I think, included a better plot. This is more or less the plot, I mean, in scale, more or less. Okay. So you'll find that for different material, the plot is, the slope is different, and at the same time, the concentration at different temperature is also different, right? So germanium has the highest carrier concentration at room temperature. So if 300 Kelvin is room temperature, so then germanium has the highest carrier concentration at room temperature. Gallium arsenide, this is a compound semiconductor, has the lowest carrier concentration at room temperature. Okay, and as I have said, this side is low temperature. So if you go this side, it's low temperature. If you go that side, it's high temperature. So as you increase the temperature, carrier concentration increases. And that probably you also have studied in your basic physics that in case of semiconductor, if you increase the temperature, the conductance increases. Why? Because the carrier concentration increases. So here also you can see the same thing, right? In the plot also it is showing the similar thing. If you increase, if you go left side of this plot, you see the carrier concentration is increasing, right? So you can see a variation of, as I've said, 10 to the power 5 to almost 10 to the power 18 at almost 1000 Kelvin. So there is a high range and wide area to play around. Similarly, as this is, remember, intrinsic, okay? These are intrinsic semiconductor. Similarly, we also will see how the carrier concentration in extrinsic semiconductor will change. So again, this is something, a representation of the same. It is not the actual plot. Okay. So in this case also you can see. Now, one thing you have to remember, if I say extrinsic, that means it has impurities. Now, for an extrinsic semiconductor, we have two different types of carriers, majority carrier and minority carrier. So majority carrier means from the name itself, it's evident that majority of the carrier is of that type. For example, say for an N-type semiconductor, what is the majority carrier? Obviously, electron. The negative carriers are high, that's why it's N-type. And what is the minority carrier in this case? Hole. Similarly, for a P-type, it's other way around. Now, in this case, let's see how the majority carrier concentration is changing with temperature. So in this case also it's reciprocal of temperature. So the axes are more or less same. Now, if I take an N-type semiconductor, as it is written, say p-doped silicon, so it will be an N-type semiconductor. So what will be the majority carrier? Electron will be the majority carrier. So we denote it in this way. So for an N-type semiconductor, this is N, that is negatively charged carrier, which is electron in this case. So it basically shows electron concentration. Then suffix N shows what type of material it is. So it's an N-type material. That's why it's N suffix N. And the 0 shows that the semiconductor is under equilibrium. Now, what is equilibrium? That we will see in few minutes. Okay. So N0 basically shows electron concentration or N-type carrier concentration in an N-type material at equilibrium. Now, what will be the minority carrier concentration? Pn0. That is hole concentration or P-type carrier concentration in N-type material at equilibrium. So if you see the trend or if you see the plot, you can understand that the entire range has an area where the concentration is more or less constant, say here, right? And if you see the room temperature, so at room temperature, the concentration of the p-type material depends on the concentration of impurity that you put inside the material. So for an extrinsic semiconductor, you have another parameter called concentration of impurity. Okay. And for a certain range of temperature around the room temperature, the concentration is constant over the temperature and we call it extrinsic range, where the concentration is constant, as I've shown here, say up to this for the first plot, then it is the extrinsic range. And if you increase the temperature from the room temperature, the concentration remains constant for a certain area. So which is nothing but a subset of the entire region. So that particular area is known as operating zone. Okay, or you can call the entire extrinsic range as an operating zone, because why I'm saying in this particular area, because in most of the cases you'll find this temperature will rise, right? From the room temperature it will rise. That's why I'm only indicating that area, but actually the entire extrinsic range is the operating zone. So in the entire extrinsic range, you can operate the device. And why you can't operate beyond that particular range? Because the concentration itself will vary significantly, which will make the entire device response very complex. And that is not the thing that we want, right? So this is how the carrier concentration in extrinsic semiconductor look like. So yeah, let us see the plot in a more nicer way. So you'll find that the plots are something like that. Okay, so here is the room temperature. So you'll find for a range, in all the cases, there is an region where the carrier concentration is, or majority carrier concentration is constant over the temperature. Okay, so this is the carrier concentration in extrinsic semiconductor, right? So you have seen the intrinsic semiconductor behavior, carrier concentration behavior in intrinsic semiconductor as well as in extrinsic semiconductor. So we will see why it is something like this. I mean, we will discuss. Just to give you an introduction, I have shown you the plots, and now the target is to figure out why the carrier concentration behavior is like this. Okay. Now, we will also see that there is a relation between minority carrier concentration versus majority carrier concentration, right? So the difference between, or the relation between these two is minority carrier concentration is equal to intrinsic carrier concentration squared divided by majority carrier concentration. So if you consider minority carrier concentration as Pn0, intrinsic carrier concentration as Ni square, and majority carrier concentration as Nn0, then it will be something like this. Pn0 is equal to Ni square by Nn0, or you can write Ni square is equal to Pn0 into Nn0. We will also derive this equation. This is the relation between majority carrier concentration and minority carrier concentration in an extrinsic semiconductor, where Ni is the intrinsic carrier concentration. Alright. Now, in this equilibrium carrier concentration concept, we will see what are the types of semiconductor. We will also see what is thermal equilibrium and steady state. I already have shown you the term equilibrium. So we will see what is thermal equilibrium and steady state. We will also see what is wave particle duality, because it will help us to understand the physics. Then in intrinsic and extrinsic carrier semiconductors, in both intrinsic and extrinsic semiconductors, we will see different properties like band model and bond model, a concept called generation and recombination, because this concept is very important as well. We need to know how carriers generate, what does generation mean, and why they recombine, what does recombination mean. Then we will see the concept of hole, the positive charge carrier inside a semiconductor, and the effective mass of carrier. Similarly, for extrinsic semiconductor also we will see majority and minority carriers, because in this case, in intrinsic semiconductor, we only have one type of carrier. I mean, the other type of carrier is also present, but when we dope it, we actually create the carrier that we want, right? So we will see the majority and minority carriers, band and bond model, and Fermi-Dirac statistics are Fermi level. This concept is also very important for semiconductor devices. Let us begin with the types of semiconductor. But before we discuss the types of semiconductor, let us see what is a bulk and what is an interface of a semiconductor. So if you consider a block of semiconductor, then the surfaces or sides of this semiconductor is what we call interface. Now the problem with interfaces are, here you may find that the atomic arrangements are not as regular as it is in the bulk, because it's interface, so you may find few defects. You may find different irregularities across the entire interface. So when we say a semiconductor, we only mean the bulk region. We ignore the interface region, because the physics in the interface becomes very complicated. So one has to understand that there is a difference between the bulk semiconductor and interface semiconductor. There are a lot of interface phenomena in a semiconductor that is a bit complex. But for this course, when we say semiconductor, we mean the bulk semiconductor. We usually ignore the interface. Okay, so just wanted you to know. Now let us see what are the different types of semiconductors. So semiconductor can be classified in different ways. First classification is a simple semiconductor and a compound semiconductor. Okay, the simple semiconductor means a single atom or element. For example, the silicon, germanium, they are semiconducting material and there are only one element and one type of atom in the material. So these are simple semiconductors. Then we have compound semiconductor. Compound semiconductors are where more than one elements are present. For example, gallium arsenide. It has gallium and arsenic. Indium phosphide. So it has indium and phosphorus. Then we have gallium indium phosphide. It has gallium, indium and phosphorus. So we can classify the materials based on whether they are simple semiconductor or whether they are compound semiconductor. Then we can also classify them in terms of whether they are pure, whether they are intrinsic, or whether they are extrinsic. So we can also classify semiconductors in terms of pure semiconductor, intrinsic semiconductor, and extrinsic semiconductor. Now, in case of pure semiconductor, what does that mean? In pure semiconductor, the molecular arrangement will be very regular. So we'll find that there is a regular arrangement of atoms in the bulk without any defect and impurity. So pure semiconductors are the material wherein atoms are arranged in a regular way and there is no defects and impurities. So 100% pure material, is very difficult to get. So you probably won't find 100% pure material in any case. So the highest purity you may get, say 99.999, something like that. But complete 100% you may not get because there will be a few defects in the material, right? So we came to the concept of intrinsic. What is an intrinsic semiconductor? Intrinsic semiconductor is there might be some defects in the material which is not exactly pure, but the concentration of carriers are same as pure. So we will get a complete benefit of a pure material as far as the application is concerned, but it's not exactly pure. So this type of variants are known as intrinsic. And then we have extrinsic semiconductor. So extrinsic is the material with defects and impurities. So sometimes we purposefully put impurities into an intrinsic semiconductor in order to make them extrinsic. Then we also can classify the semiconductor in terms of their band gap. So if there is direct band gap semiconductor, there is indirect band gap semiconductor. Okay. So direct band gap semiconductor means when the conduction band and valence band are in the same location of or at a same k value, that is wave vector value. Then we call it direct band. So I think, so I have the representation. So if this is the conduction band and if this is the valence band, you'll find that both the conduction band and valence band are present at a same k value. So minima of conduction band and maxima of valence band are at same wave vector value. This is known as wave vector or propagation constant. Okay. So I will discuss these band diagrams also in this course, but just to give you a feel for the direct and indirect band gap, I am just showing it. Okay. So this is and energy versus this side is energy, this side is K, right? So this is how an direct band gap semiconductors look like. For example, say silicon is a direct band. Oh, sorry, yeah. So you'll find direct band gap semiconductors. There are many examples of direct band gap semiconductors. At the same time, you'll also find indirect band gap semiconductor wherein the band gap, this conduction band and valence band are at different locations. So silicon is an indirect band gap semiconductor, okay? So it's not direct band. So you'll find that the conduction band and valence band both are at different wave vector values, at different propagation constant. Both of these has their own uh, advantages. For example, if you want to make a photovoltaic device wherein you want the carriers to be separated for a longer duration, it's better you use an indirect band gap semiconductor, because in that case the recombination will be very difficult and it is very easier to make that uh, separation between the electron and holes. However, if they are direct band gap, they are more likely to recombine, so they'll come down very easy. So there are different things associated with that. So I'm not going much in details at this moment, but this is how it looks like. Okay. So that's why you will find silicon based photovoltaic devices. That is one of the reasons. Silicon based solar cell. Okay, you'll find because silicon has this indirect band gap property. Now let us start. What is thermal equilibrium? Now equilibrium is a very important concept and we should know that concept very very nicely so that we don't get confused when we come across that term. Now there is a trend or an approach to solve complex real life situations by considering them a small deviation from convenient ideal situation, which is treatable using mathematics. In physics, this is one of the approach of solving problems. So what we do is, if there is a complex problem, we figure out what is the very close idealized situation, or what is the idealized situation associated with that complex problem, which is approximately very similar to that, and then we consider a small deviation from it. It's just like a landmark. When you tell an address, you say a landmark. For example, if you ask one of your friends to come to the canteen, and if he is, for example, say LHC canteen, and if he is not quite aware of where is the canteen, then what you say? Okay, you come near the library, and then you'll find, if you go straight or if you go in that direction, you'll find the LHC, and behind that LHC we have the canteen. So something like that. That is how you generally communicate with someone when you are planning to tell them what is that exact location. So this is similar to that. So you go to a landmark, an idealized situation, and then you consider a small deviation from it. This helps in solving complex problems. Okay. So in this case, the small deviation is known as the quasi-equilibrium. We call it quasi-equilibrium. It's not equilibrium. And equilibrium is the convenient ideal situation. This is what the equilibrium is. So what we do is, we start with an equilibrium situation and then we consider a small deviation so that we can solve the complex problem. Okay. Now, we call a semiconductor in equilibrium with respect to the environment So always remember, equilibrium has to establish between two different entities. When we say that a semiconductor is in equilibrium, we mean that it is in equilibrium with respect to the environment. Okay. So we call a semiconductor is in equilibrium with the environment when whatever process is happening inside the semiconductor or outside the semiconductor, it should have a reverse process at the same time. What does that mean? So if an semiconductor is in equilibrium, the processes that is going around the environment and the semiconductor, all these processes should have a reverse process at the same rate. Not only with the environment and semiconductor, but also inside the semiconductor. For example, if 10 electrons are going from left to right, 10 should go from right to left, something like that. Each process should have a reverse process at the same rate, which is known as principle of detailed balance. And what does that detailed balance mean? Detailed balance means if you look into this process, even in a more detailed way, as detailed as possible, there should be a balance. For example, if I say out of 10 electrons, 5 has 1 energy, 2 has E2 energy, then also in the reverse process, 5 should have that energy and 2 should have E2 energy, something like that. So you should consider all these processes in a detailed way, and there should be a balance in each possible details. So that is what the equilibrium is all about. So I repeat, in case of equilibrium, you will find that there is many processes associated with a semiconductor, but if the semiconductor is in equilibrium, there will be a reverse process at the same rate. Okay. Now, one thing one should understand that in equilibrium, there might be a lot of processes going on. When a semiconductor is in equilibrium, there might be a lot of processes that are going on. But the thing to be noted is, the point to be noted is, in this case, it doesn't matter what is going on, but there should be always a reverse process at the same rate. That is what is very important, right? So as I've said, the detailed balance is very important. Detailed balance means at all possible detailed investigation, the balance should hold. So that is what an equilibrium is all about. Now, as I have said, that there might be a lot of processes already going on inside a semiconductor, even if they are in equilibrium. That's why it's not a static equilibrium, it's a dynamic equilibrium. Now, there are two criteria, major criteria for a thermal equilibrium. Okay, one is there should not be any external excitation other than temperature. For a thermal equilibrium, the first criteria is no external excitation other than temperature. And the second criteria is no net motion of charge and energy inside the material. These are the two criteria we generally look on in order to decide that whether the material is in equilibrium or not. Okay, because we need some criteria, right? Otherwise, how do we decide whether the material is in equilibrium or not? We understand what is in equilibrium. At all possible detailed investigation, there should be a reverse process at the same rate. That is what will ensure that the material is in equilibrium. But in our case, when we look into a semiconductor, how do we decide whether it's in equilibrium or not? We can't go and check all the details. So there are two criteria that generally we look after. One is no external excitation other than temperature. Second is no net motion of charge and energy. So the word net in this case is very important. Why important? No net motion means there might be motions. There might be a huge activity inside the material, but that must be balanced by the reverse process. That's why we call it dynamic equilibrium. It's not static equilibrium. It's not something very static. We don't mean that entire process is frozen. Nothing is happening inside. A lot of things are happening, but there is a reverse process. So always remember that the word net is very important. So we should say no net motion. It's not like no motion of charge and energy. There might be motion, but there should not be any net motion. Okay. So if you take an example, for example, here, you take an example of a semiconductor block where one side has T1 temperature, another side has T2 temperature, which is higher than T1 temperature, then whether this is in equilibrium or not. So this will not be an equilibrium because we know that heat energy will flow from higher temperature to lower temperature. So it's a non-equilibrium case. So the second criteria doesn't satisfy, right? Similarly, say if you put a power supply across this semiconductor, it will be in equilibrium? It will obviously not be in equilibrium. The first one itself is not satisfied. So there is an external excitation, that is potential we are applying. So it's not there. So if a semiconductor, now it's very interesting to see that if a semiconductor is visible, that means if you keep a semiconductor under light, then there is an external energy, optical energy there, right? If you can see a semiconductor, that means light is reflected from that semiconductor. That's why you are able to see that particular material, right? So if you can see a semiconductor, there is always an external excitation, that is light. So the semiconductor is not in equilibrium. So if you can see a semiconductor, it's not in equilibrium. So it's very difficult to get a semiconductor in equilibrium condition. You have to put it in the dark, and a lot of criteria has to be maintained. So it's very difficult in practice to get equilibrium condition. So equilibrium does not exist in practical situations in almost all the cases. That's why we bring in the concept of quasi-equilibrium. Quasi-equilibrium means small deviation from the equilibrium, right? I also have said while I started the discussion, a small deviation from the ideal situation. Equilibrium is the ideal situation which you probably won't get so easily. So the quasi-equilibrium term emerged, right? So here, for example, say if you have a PN junction, and if the PN junction is in equilibrium, you'll find the current density from P to N is equal to N to P. These current densities are balanced. But if you put the PN junction, or if you connect the PN junction with a voltage source, then you will see that in one direction the current density is higher, in other direction the current density is lower, so you will get a net current density, right? That is what we mean by dynamic equilibrium. You have current densities in this case also under equilibrium, but they are same, so there is no net current. But when you put an excitation, you will find that there is a difference which gives you a net current density. So that is what an equilibrium is all about. The next concept is steady state. Many a times people think equilibrium and steady state are same, but they are not actually same. In case of steady state, all the processes are constant as a function of time. So with time, processes should be constant. In this case, reverse process is not mandatory, but all the processes should be constant. So if you look at the equilibrium and steady state, it's something like that. Equilibrium is a subset of steady state. In case of steady state, reverse process is not mandatory. But even if there is a reverse process, you can call it steady state. But even the reverse processes are not there, but all the processes are constant as a function of time, you can call it steady state. That's why steady state is the superset, equilibrium is a subset of that steady state. So all steady states are not equilibrium, but all conditions that are in equilibrium can be called as in steady state. Okay. So the steady state also has a similar term called quasi-steady state or quasi-static condition that you will find in many analyses. So mostly in transient analysis, you will find that people write in quasi-static condition or quasi-steady state condition, but the idea is same. The idea of quasi is same, a small deviation. Okay, so that is what the steady state is all about. So in this lecture, we already have studied the carrier concentration in intrinsic and extrinsic semiconductor. We have seen how this extrinsic semiconductor concentration or carrier concentration in extrinsic semiconductor and carrier concentration in intrinsic semiconductor, how it changes with respect to temperature inside a semiconductor material. We also have seen what is equilibrium, how equilibrium can help us to solve certain sort of problem, why we should consider equilibrium as the initial starting point of a certain problem. We also have seen what is steady state, how steady state is related to equilibrium or how they are different. So after all this discussion, we now have a comprehensive idea about carrier concentration. We now have some understanding about equilibrium and steady state. Now in the coming lectures, we will cover few more important topics that will be really interesting to know, and that is very important also to know when you design a semiconductor device or a sensor related to semiconductor device. Thank you.